Hello. This is the chapter 17 and 18 from Solomon's. I've had to cut down the material in order to be able to finish it up for the spring 2019. So this is a little bit shorter slide deck than the previous one. With that, so with chapter 17, we're going to be talking about carboxylic acid derivatives and some of the chemistry that we can do with that. And then for the chapter 18, we're going to be talking about the fact that a CH bond right next to a C double bond O is going to be incredibly acidic, and you can use that for as a carbon nucleophile, and traditionally it's in order to be able to make new carbon-carbon bonds. With that, so these are some of the carboxylic acid derivatives we're going to be talking about. Acid chlorides, acyl chlorides or acid chlorides. So they're traditionally made from carboxylic acid, so that's where the name comes from. Anhydrides or acid anhydrides, again, those are usually made from carboxylic acids. Esters and nitriles, thioesters, right? So the thio is typically means the sulfur version and stuff like that, and that's exactly what it is. It's the sulfur version of the ester. The amides are, right, they're going to have the nitrogen here, and it doesn't necessarily matter if there's how many hydrogens there are. There's just going to be three things hanging off of that nitrogen, whether they're, or excuse me, two things besides the C double bond O, whether it's hydrogens, one hydrogen and something else, or no hydrogens. As far as for naming of the amides, we're going to follow the normal 4 steps with that. So, but these are actually make some sense. So with that, so when you have an amide, right, you're going to have the part that is the part that's going starting at the C double bond O and going away from the nitrogen. That's going to be the main chain, no matter what it is. Okay, and then and so in this case you would have four carbons, right? So with that, so you have the main chain is going to be C4, which would normally be butane, right? But for to indicate that it's an amine, or excuse me, it's an amide, you replace the E and you add in amide, so it becomes butanamide. Not too bad. Now, any of the side chains, so let's say we had a methyl group here, so we have a methyl here and an ethyl there, right? So with that, so we would have a methyl and an ethyl. The hydrogen hanging off the nitrogen we don't care about. So with that, but the numbering is always going to start here at the C double bond O, and again go away from that nitrogen. So it's 1, 2, 3, 4, right? So that means that the nitrogen is, or the methyl group is going to be hanging off of carbon 3, but obviously it's not part of the main chain. So how do we indicate that this ethyl group, right, where that's hanging off the nitrogen? Well, you do that by instead of putting a number, you put N to indicate that it's hanging off the nitrogen. Okay, so this functions like any other like a number. Something like that. So because you're going to want to put ethyl before methyl, right? So it's going to be N-ethyl, right? And the 3-methyl, 3-methyl butanamide. This particular one. Okay, not so bad. Here's another example. Oh well. So it's very similar to what we just had, right? That's what happens when I try to make one up on the spot, right? So this right here, starting at the C double bond O and going away from the nitrogen, right? It's 1, 2, 3, 4. Forgot that. Right, so again, it's going to be C4, right, butane to butanamide. Right, and again, our side chains, right, are going to be, right, we have a methyl, an ethyl, and a propyl. Right, so the methyl's hanging off of 3, the ethyl's hanging off of the nitrogen, and the propyl is also hanging off the nitrogen. So you put it in alphabetical order, right? So it'd be N-ethyl, right? And then next one up is the methyl, right? Because it's ethyl, methyl, propyl. So 3-methyl, N-propyl, butanamide. So there you go. Now, esters, these things are a royal pain in the neck. And it has to do with a historical quirk for how these things used to be put together. Okay, they used to take a carboxylic acid and an alcohol and put them together. That's the classic way of eating them and distilling off water, and then there you go, stuff like that. So, but the way that they named it is they would name it with the alcohol and the carboxylic acid. You put the name in front. So if you had, say, this ester here, right? So let's do it like that. I don't know. Let's do this one as an example. Just like the the amide, right? The main chain is going to be starting at this C double bond O and going away from the other oxygen. So it's going to be 1, 2, 3, 4, 5, 6. Okay, so you got to find the longest chain extending away from, starting at that C double bond O and going away. And so this side is going to be the main chain, right? So C6, so it'd be hexane, but the main chain goes to O8, so it'd be hexanoate. Sometimes it's 8, sometimes it's O8. That's what happens better, right? So that, and so you also have this side chain ethyl, right? That's hanging off of carbon 3. Okay. So that's the C double bond O side. The O side of the ester, so this part here, okay, it's right, so 1, 2, 3, 4, 5, okay, so that part there is always going to be listed, right, so C5, it's going to be listed as if it were a side chain, okay, so pentane goes to pentyl, right, just like methane goes to methyl, ethane goes to ethyl, you know, propane goes to propyl, okay. Pentyl. Now, the way that this, so this side here is going to be pentyl, and this name always has to be listed first, okay, no matter what it is. That's why I like parentheses, so we just bolt whatever this is to the front, and then the rest of it is that part there. So it'd be pentyl, 3-ethyl, hexanoate. Okay, and notice we don't mix these two together. We don't. It's not 3-ethyl pentyl hexanoate. Okay, the pentyl just goes out front no matter what it is. Okay. Oh, here's another hexanoate. Right, so 1, 2, 3, 4, 5, 6. Right. So. I'll put the dots in so you can see it. Right, so NO, Cl. Okay, so the O side, right? So this is, it's 2 carbons, which would normally be ethane, but we consider it to be a side chain. It's named as a side chain, so it becomes ethyl. So this side is going to be ethyl. This side here, from the C double bond O, right? We extend out. We start the C double bond O and extend away from this oxygen. So 1, 2, 3, 4, 5, 6, right? So C6 becomes hexane. and they indicate that it's an ester, you go hexanoate. Right? We also have a nitro group right at carbon 2, right? Because again, the numbering is going to go away from the starting at that C double bond O, and then the we also have a chlorine atom, so it's chloro, it's at 4. So this part here, right? Chloro comes before nitro, so it would be 4 chloro, 2 nitro, right? Hexanoate. That part is from here. And then what you need to do is then put the ethyl group out front. Again, no matter what it is, it goes out front. Okay. So again, parentheses you can sort of see the two parts if you put them in parentheses. So okay, so one of the the general class of reactions that we're going to be dealing with are what are called acyl substitutions. Okay, so they're very similar to like an SN2 where a nucleophile comes in and a leaving group goes away. Okay, so you're going to have, let's say, something like this. You're going to have some sort of nucleophile, right? And it has to have a lone pair, right? Just like with SN2, it doesn't have to have negative charge. It just has to have a lone pair. Okay? Because remember, this is a polar covalent bond, so partial positive, partial negative. So this lone pair on the nucleophile is going to want to attack the partial positive on the carbon. Carbon can have 4 bonds, so the easiest way to get rid of that bond is to push it onto the oxygen. Okay? When that happens, you get your tetrahedral intermediate. Okay? But what the molecule doesn't really want to be in this form. Okay? So what it wants to do is it wants to collapse this back down to C double bond O. And you can do that if this is not a carbon or a hydrogen. Okay? If it is, we'll talk about what happens in that instance in a bit. You're going to want to collapse this back down, but again, a carbon can have 5 bonds, so it's got to get rid of something. And so, I mean, it could kick off the nucleophile to go back to here, but that's not a productive reaction. It's not going to break a carbon-carbon bond, so the only option we have is the chlorine. And just like with an SN2 reaction, right, the leaving group, it's going to be a leaving group. It goes away. It's going to take the electrons with it, and so you're going to end up with this. Then your nucleophile plus Cl. Now, sometimes if there's a hydrogen here, what can happen is the leaving group can swipe a hydrogen off your nucleophile as it's leaving, stuff like that. But in this general case, we don't have it. Stuff like that. So but the nucleophile substitutes for the leaving group here, just like it would have for an SN2 reaction. Okay, so this is what we're going to be talking about for the next few slides, just that reaction. Okay, so if you had, say, a water, right? So the lone pair is going to come in, push this up. You're going to get the tetrahedral intermediate. This is going to collapse down, kick away the chlorine. I usually say the chlorine comes in, but I suppose another water molecule could as well. This comes in, grabs the hydrogen, and so you're left with your nucleophile missing a hydrogen that was originally on it, plus something like HCl. Okay? Stuff like that. So, or this plus the chloride. Stuff like that. So either way. Okay. Now, if the your nucleophile comes in, okay, and let's say you either have an aldehyde here, so you have a carbon here or a hydrogen, or a ketone where there's 2 carbons. In order for you to collapse this down, okay, well, I guess it could kick off the nucleophile, but again, that's going back to starting material. There's no way that we can break a carbon-carbon bond or a carbon-hydrogen bond, so it's stuck. Okay, we can't go to the C double bond O side, because what you would need to do is either kick off a hydride or kick off a carbanion, and those are really nucleophilic and basic, things like that. So what ends up happening is this turns into, during the workup at the end of the reaction, this part here becomes an OH. So what you would have is, if you had, say, acetone, and you had a hydride source, so say lithium aluminum hydride, that's going to attack here, that's going to kick up to make your tetrahedral intermediate like this. But the problem is, if this collapses down, it's not going to break a carbon-carbon bond, it's not going to break nor this carbon-carbon bond, and it's not going to break this carbon-hydrogen bond, so it's stuck. So this ends up turning into an alcohol. So somewhere along the way you dump in water, and it grabs it. So you would get this molecule. So if it ends up being stuck like this with the O-, it's going to grab a hydrogen from something and turn into the alcohol. So be careful. Now this is a list you're going to want to know. Okay. So these are the different derivatives. Okay. Now you can go down this list from reactant to product. Okay. So an acid chloride can go to a thioester, or an acid chloride could go to a regular ester. Okay. Or you can go across, sort of like, so from one ester to another type of ester, or an ester to a carboxylic acid is basically an OH, something like that. Or from one type of thioester to another, no problem. What you can't do is go up the list. Okay, you can't go from thioester to acid chloride. You can't use a thioester to go up there. Okay, you can't go from an amide to turn that into an ester. It's going to take a lot of work and a lot of heat, and probably won't work at all. Stuff like that. So you need to know not only what these compounds are, but the order in which they are. There's just 5. It's not too bad. Something like that. So to know that they can either go from side to side, or they can go down. Something like that. But they can't go back up. Okay. And so these are the different types of reactions that we can talk about. This is the reduction where you hydride, so you end up with the alcohol. Or this is what's called a Grignard reaction, where you have a carbon nucleophile. You would also get a OH group there. Okay. So the way this works, right? So you have the lone pair nucleophile comes in, the attacks here, kicks up, collapses down, and kicks away your leaving group. When this is leaving, right, it's going to snag a hydrogen for the where this is at, right? So it goes from NH2 to NH, right? And this second H ends up on HCl. So that's how they all work. Okay. So here's the mechanism here. Okay. So if we'll predict the product. Okay. Right, so this lone pair is going to attack the carbon. We're going to go up, collapse back down, and we're going to kick that away. Something like that. And so the product, and as that's leaving, it's going to snag that hydrogen. So we're going to end up with like that, plus the oops, colors are backwards. Right, so this H here is this H, right? All we're doing is we're snipping that bond. So this methyl group here is going to stay with that sulfur, right? Anything that's hanging off of here we're not messing with that bond. The only thing we're breaking is this carbon-sulfur bond. Okay, so if you have something, right? So if you have it here, right, you snap it, right? We didn't do anything to the to this clip, right? So it's still going to stay with this part. Okay. The other thing is, right, we're going from a thioester, right, to an ester. And if you look back, that's fine, right? Thioester to ester. So we're okay. So for this one, right, so for NH3, right, so this lone pair is going to attack here, right? Go up, collapse down, kick that away. As it's going away, it's going to snag one of the hydrogens, so you're going to end up with like that. And again, we're going to go from ester to amide, and that's fine because amide's going to be the most stable of it, so we're good. Okay, so for here, okay, we have an anhydride. It's a symmetrical anhydride, which is all I'm going to give you on stuff like that. If it's mixed, so if the group over here is different from the group over here, where you're going to get attack is going to be on the less sterically hindered side. But for this case, where it's symmetrical, it doesn't really matter which one you attack. So just out of habit, I'm going to attack here. It's going to go up, down, kick away, and we're just going to break that bond, so this whole thing goes away. And so what you're going to end up with is, and again, as that's leaving, it's going to snag that hydrogen, so you're going to end up with S. Right, 1, 2, 3, 4. Right, 1, 2, 3, 4. Plus now it looks a little weird, but it's no different than all of these reactions are exactly the same, right? Here's your leaving group, here's your leaving group, here's your leaving group. There you go. And again, we're going to go from an anhydride to a thioester, which if you look back, we're going to be fine. Okay, so there we go. Now for this one, right. Right, we're going to have this lone pair come in, attack here, up, down, kick away, and it's going to snag the hydrogen as it's leaving. Right, so we're going to end up with like that. The problem is we're going from an amide to an ester. So that means this reaction isn't going to happen because it's going. If I go back quickly, right? We're going from an amide to an ester. Not going to happen. Not readily anyway. So no. So in fact, this is going to be no reaction. So you got to be careful. Okay. So the question is, like, where do we get the acid chlorides if that's the highest? Well, you have to use this compound called thionyl chloride. It's SOCl2. It is the so what it does is it actually activates. So you start with the carboxylic acid, and thionyl chloride's sole purpose in life is to turn OHs into Cl. So it doesn't matter if it's an OH on a carboxylic acid or an OH on an alcohol. It's going to turn that OH into a Cl, and it does it by making an ester that's even more reactive than the thiochloride or than the acid chloride, so that the chloride can come in and do a second attack and kick away that leaving group, which then decomposes into SO2. So it stinks to high heaven. It smells like rotten eggs, or burning brimstone. Actually, I guess technically. So it's not. It doesn't smell good, but this is a gas, and so it bubbles away, and so that helps drive the reaction forward. So with that, so these are still going to be very reactive, but you have to. It's kind of hard to you generally make them as you need them, with that. But the thionyl chloride is a nice molecule to do. Okay, so that was chapter 17. Okay. So for chapter 18, we're going to be talking about, just as a reminder for the acidity of CH bonds. So a normal just alkane CH bond is going to be pK of about 44. If you go down, if you look at the terminal alkyne, remember that was from a few chapters ago. It's substantially more acidic. So it's not like twice as acidic. It is one with 19 zeros behind it. So I don't know. It's like billion times more acidic, or I don't know, trillion or something like that. More acidic, somewhere under there. More acidic for this. Now, even then, having a regular CH2 next to a C double bond O is even 10,000 times more acidic than even the alkyne. So this is a very easy hydrogen to remove, stuff like that. And so and the reason for that is it all has to do with resonance. So if a base comes in and plucks this away, these electrons have to go somewhere, so they end up on the carbon. Well, they end up here, but we can do a resonance structure where we make a double bond here and kick those up. And so this is this helps stabilize that carbanion. So since we have a stabilized carbanion, we can use that to do SN2 type attacks, SN2 attacks really. Okay. And so, technically it's not in this. This is the enol form of that. So you sometimes hear me call it enol form. So the OL is for the alcohol. That's the ending for an alcohol, like ethanol and methanol and isopropanol, things like that. The ene is for that double bond for the alkene. The keto form is like this, and because it's a ketone, so by that we call it the keto form. Okay. Just as a reminder, okay, when we hop between these two, they're not resonance structures, right? Because the hydrogen is moving, right? This going from an O to an OH, hydrogen's moving. This isn't resonance. It's an actual equilibrium. Okay. With most of the time, right, it's going to prefer to be in this keto form where it's a C double bond O, right? That's why the reactions in the previous chapter wanted to collapse down. It's because this is a much more stable form. Okay. So it's going to be extremely small. Okay. The exception for this, okay, is if you have this diketone, beta diketone. So if you're looking at here, this is the alpha position, and then 2 away would be the beta position, and then this one right here would be the gamma position from there. So like that. So we said before it was incredibly easy to take this away. Well, if you have 2 of them, right, it's even more it's even more likely, right? And the reason for that is, well, I should say we're not to there yet. I'm sorry, I got ahead of myself. This is actually one of the few times where the enol form is actually preferred, because we can get hydrogen bonding here, and you can also extend out the resonance, right? Notice this double, single, double, stuff like that it allows it to do. Plus you get the hydrogen bond there, which is very stabilizing. So in this form, it's fine. It doesn't necessarily mind being in that double bond, and because of that, you can use that acidity. Okay, so getting back to these nucleophiles, right? Remember, we're next to a C double bond O. It's very easy to take off that hydrogen with LDA, lithium diisopropylamine, or amide. No, excuse me, analide. Or no, it's not analide. Anyway, LDA. It's a very strong base. It's very similar to sodium amide. So like that. So I guess it's isopropyl amide. So anyway, it's a strong base, and so it can pluck off that hydrogen, and this carbanion can come in and attack, kick this away. And so what we've done is we've made a new carbon-carbon bond here. Same thing here, the LDA, this gets ripped away. This carbanion can come in, attack the methyl group, kick that away. Okay. So one way we can do this is an SN2 attack. Okay. We can also do an SN2 attack if you just have a molecular halide. Okay. And so if you have something like this, right, you hit it with LDA, right? It's a base. It's gonna grab that, put those electrons there. Oop. Right. What can happen is if you have something like bromide, it also happens with chlorides and iodides and fluorides. This is going to come and attack there, and then kick this away. Just like what was going on here. Just instead of a carbon group, it's just another halide. And in doing so, what it allows you to do is it allows you to put in a bromine or some sort of halide in that position. So it works pretty well, plus Br minus. Okay. Works pretty well. Don't worry about this. This was actually confusing. Okay. So if we have this, as far as predicted products go, okay. So if we have this, so this is the only time you see LDA. Okay, you know, so it's a base, right? So what it's going to do is it's going to take the most acidic hydrogen is right here, so it's going to take one of these hydrogens away and put those electrons there, and so you end up with right there. And then this you can use as a nucleophile to attack here, to do an SN2 attack. Push that away, and so you're going to get, so here's our carbons here, 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 and here. So we're going to make a new bond between this carbon and then that carbon where the halide was, just like every other SN2 attack. So here, like that. Okay. Now with this one down here, we have now again we're going to do sodium hydroxide, right? So it's got a base, right? There's no hydrogens on this side, right? It's all carbons. Okay, but so again, this is going to take that, kick that, you know, extract the hydrogen. So those electrons end up on that carbon, so you end up with this. And then if it sees, and then let's say, so we've got what, iodine, so right, so you have iodine, you get this nice SN2 attack. Oops, that's a negative charge. There, kick that away. Oh, this would have been plus H2O. So what you're going to have is H, and then you have an iodine, double bond O. You get your benzene plus I minus. Okay. There you go. Now you can do more synthesis with this. It's a little bit easier to do it if you have the diketone, right? So with that, so this is, if you have one ketone, right, it's going to be the pKa of about 20. If you have two ketones, it's going to be a pKa of 10. So we're not talking about you know, that it's twice as acidic. So that, no, it's 10 to the 10th, right? So that's what, 100, you know, like 10 billion times, something like that. That more acidic, okay? It's all because of the fact that it's got additional resonance structures that it can do. If you have two C double bond O's as opposed to one, okay? And it turns out acetoacetic acid, so ethyl acetoacetate, which is this molecule, is pretty cheap. So if we throw in some sort of inexpensive base like the sodium ethoxide, and really what you want to do is you want to match it up with this one. So if you get nucleophilic attack here, up, down, here I'll show you. So let me draw this out. So you try to match these things up. So if your base decides it wants to be a nucleophile, okay. So this is your. So if this attacks here, up, down, kick away, which it certainly does, okay, it's what you're going to get is O-ethyl, right, plus like that. So this one here is this one here, right? That one there is this one here. So it's just swapping it back and forth. So if you match these up, there's not going to be, it's not productive for it to do this. Okay, so what you're going to do, so what happens instead is it's going to act like a base. When that happens, your O-ethoxide, okay, right, it's going to come in here, grab that hydrogen, put those electrons there. No different than what we've been doing before. We're really only learning one reaction in this chapter, right? Plus, I guess, ethanol. Okay. If we dump in some sort of the alkyl group, so let's say this, right? So a butyl, right? This guy can come in here, attack there, just a normal SN2 reaction. And so what you would end up with is like that. And voila, we've made ourselves a new carbon-carbon bond. So you can go through this cycle again, stuff like that. So let's say you threw in more sodium hydroxide. After you made this, you threw in more sodium hydroxide, right? This could come in and grab that. Right? That goes up here, right? So you're going to end up with O-ethyl, right? And let's say you put in, I don't know, benzyl bromide, right? This is going to attack here, kick this away, and so what you would end up with is this one, right, that you put on first, and then here, right, because there's a carbon right there, right, you can put on another one. So you can actually put two groups onto here. Oh, forgot this. Okay. So as an example, okay, so we have our ethyl acetoacetate. Now, again, for predictive products, you don't have to draw the mechanism, but I usually do because I think it makes things a little bit easier. Okay, so the first thing we're going to do, right, is dump in some base. This is going to grab that hydrogen, move those electrons there. Okay. So we're going to make this. Right, so if we then dump in ethyl bromide here, right, we're going to get an SN2 attack, kick this away, Right, so we're going to get this 2-carbon piece there. Now the right, so we still have a hydrogen here. It's still next. It's still between two C double bond O's. So we can again go through this process again as sodium ethoxide. Right? This is going to come in, grab this, push those up there. Right? Right. Now, in this case, right, if we put in, say, methyl bromide, right, we can do this SN2 attack. It's going to attack there, kick that away, and so what you would be left with is this. Oops, like that. Okay, so we just had to run through this cycle twice, and the first time we put on this ethyl group, this 2-carbon ethyl. Oops. The other time we can do this. Now that's fun, right? Because we just made 2 new carbon-carbon bonds pretty easily. Okay. But what if we didn't want to have this? Okay. What if we wanted to do more things to it? And it turns out that if you run this through a base step, so you just dump in sodium hydroxide. Okay, what it does is the hydroxide literally, right, it comes in here, up, down, kick away, right, just from chapter 17 stuff. And so what you end up with is that. Now, okay. Now, if you dump in acid, okay, and heat, this will actually decarboxylate. Okay, there's actually supposed to be a hydrogen here. I don't know why it got cut off. Stuff like that, but it decarboxylates, stuff like that, and so this goes away and turns into CO2, and so what you end up with is this. So hydrogen remains, it ends up going there. Okay. So this part here, you know, so this CH3, this C double bond O, and most importantly this CH2 came from this part up here. Right? So that CH2 is this CH2 there. This 2-carbon piece here came from here. This CH3, right, came from here. Okay? So I'm just showing you where the different parts came. Now, so this is right. So you go in, you do your doing this, and then you run it through sodium hydroxide and then acid, and then it decarboxylates, and you end up with this. Now, if you want to draw it like that, that's fine. If you want to draw it, be all fancy and draw it like that, that's also okay. Right? So that's all we did here. So you end up going, you know, you make the product that we did earlier, right? You run it through sodium hydroxide. That turns it into the OH, the carboxylic acid here. You dump in acid and heat, and that whole group goes away. Okay. Now the other thing that you can do, okay, so instead of using where this is a ketone on one side and an ester on here, what you can do is you can use what's called malonate, which is a diester. Okay, diethyl malonate is pretty darn cheap. Okay, but it works exactly the same way as all the other reactions in this chapter, right? You're going to have an acidic hydrogen here, right? You dump in base, it's going to rip it away. Put the lone pair up there, which then you dump in your bromide SN2, then you're going to make a new carbon-carbon bond. Now, the interesting thing is that, okay, so let me walk through this. Okay, so we did our sodium hydroxide or sodium ethoxide. right? This is going to grab that, move that there. Now, okay, so when we dump in our 1, 2, 3, 4, our butyl bromide, right? There's a 4-carbon piece, right? This carbon nucleophile is going to attack there, kick that away. So we're going to have hydrogen and then our 4-carbon piece. Well, and bromide. Okay. Now, if we run through that sodium hydroxide, or in this case, potassium hydroxide, okay, there's going to be a lot of it around. Okay, so we do a hydroxide step and then an acid step. So we're going to dump in hydroxide. Okay, and since there's a lot of it in there, it's actually going to attack both here, up, down, kick away. It's also going to attack here, up, down, kick away. And so what after the hydroxide step is you're going to end up with this. The dicarboxylic acid. Okay? And then when you run it through the acid step, okay, this is one of these, it doesn't matter which one of these is going to go away. It's going to decarboxylate, just like what happened over here. Okay, after the hydroxide step, it turned into carboxylic acid. We dumped an acid, and that went away, right, as CO2, which is going to go away. Same thing happens here. One of these is going to go away. Oop. OH. Well, it's going to turn into a hydrogen, and then you've got here. Let me redraw this. That's going to go away and leave behind a hydrogen, and then you're going to have your 4-carbon piece. And there you go. So if you wanted to have a methyl ketone here, you would start with the acetoacetate, ethyl acetoacetate. If you want to leave with carboxylic acid here, you start with the diethyl malonate, esters on both sides, right? And this you can take on to do all that other chemistry that we were doing in chapter 17, something like that. So again, you can do it twice, right? Because there's 2 hydrogens there, so you can go through a second cycle, decarboxylate, and you end up with that. So it's nice for making what is it? The highly steric, or highly substituted carboxylic acids. Okay. Now, if we want to go backwards, okay, if we say, okay, I want to make that one there, so with that. So I'm going to start with diethyl malonate, okay. The trick is to figure out where all the carbons are coming from, okay. So don't forget that that's a CH2, and what you're going to need to get to is a 1, 2, 3, 4, 5, 6, 7, 8, okay. Okay, this is the tricky part. First thing you need to do is you got to figure out where these carbons are. So remember, we're going to end up going through right. There's only one C double bond O left, so we would have had to have gone through that decarboxylation step. Okay, so this carboxylic acid is probably going to be coming from that carboxylic acid here, or that one. It doesn't really matter. This CH2 here, okay, is this CH2 here. Okay? Right? It's the one right next to that C double bond O. What we lost was another one of these, right? So this was originally the ethyl, right? So this, that this 3-carbon piece here is this 3-carbon piece here, right? But really we only care about, you know, or however you want to do it, 2 of these carbons. Okay, that's the only 2 that stick around. So what we need is we need a 2-carbon piece here and a 1, 2, 3, 4, 5, 6-carbon piece here. This CH2, right, don't include that in there. That's coming from this malonate. It's right there. Okay, stuff like that. So be careful. So we're going to have to go through this cycle of base, add an alkyl bromide, and then with that. So I don't care which one you put on first. Right, so you're going to want to put in sodium ethoxide. Right, it's going to grab one of those hydrogens, put this up. Right, and so let's put on. So now let's put on this one here. Right, so we're going to need to put in a 6-carbon piece. Right, so 1, 2, 3, 4, 5, 6 with a bromide. So that is going to attack there. Kick this away. So we're going to end up with a 6-carbon piece onto it. 1, 2, 3, 4, 5, 6. So I use the dots for this one just to keep things straight. So we're going to go through this cycle again. Right? So we're going to add the sodium ethoxide. Right? That's going to grab this, move those electrons up there. Right, and that 6-carbon piece is still here. Okay, and then we need to add this 2-carbon piece there. Right, so it's going to attack there, kick that away, and so now we're going to end up with this. One, 2, 3, 4, 5, 6, right? And then 1, 2. Now the next step is this. You're going to dump in hydroxide. Right? It's going to be a lot of it. So right, we're going to attack here, up, down, kick away, and here, up, down, kick away. And so what we're going to end up with is OHs here. And then don't forget the 2-carbon piece over here. When we dump in acid, right, we're going to kick one of these things away, and we're going to end up with this. Okay, so here is our main chain, and I kind of color-coded where things are coming from. Right, so here's the main chain. Right, we have the first 2 carbons are coming from our malonate, this one and that one. Okay, and then 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. And then also hanging off of here, there's this 2-carbon piece there. But this is the process you go through for every single one, okay? Every one of these things. So there you go. Good luck.